So let's talk a little bit more about antennas. And one of the most things to realize about an antenna, which a lot of people get confused on, is that antennas are passive, i.e., they don't increase the power or boost the power in any way. What they're simply doing is taking the electrical energy and then convert it to RF waves. However, the pattern that it forms when it propagates over the air is dependent on the antenna. And those different patterns are very important to understand in a wireless LAN. For instance, cover a floor, then you want a circular pattern that's going out and radiating across a floor. If you're trying to connect two buildings, then you want a pattern which is much more of a long lobing pattern. So you want to focus your energy into a narrower beam. Now, when you describe an antenna, those qualities then define how they actually create those radiation patterns over the air. So antennas are designed to operate at certain frequencies. One of the key attributes of an antenna is the wavelength. So a higher frequency, a lower wavelength actually will require quite often a smaller antenna. And then a lower frequency at a higher wavelength sometimes requires a larger antenna because they're designed to operate at different frequencies and the antennas are designed around the wavelength. When you describe the radiation pattern that's formed, we talk about the beam width. So for instance, if I was wanting to deploy an access point on a wall and maybe I want 180-degree coverage, then I'd want a beam width of 180 degrees. If I was going between buildings and I wanted a narrower beam, then I'd define a beam width maybe of 30 degrees. So we describe antennas in terms of beam width and also the gain. So if I'm able to focus my energy into a narrow beam, my energy is going to go much further, much as if you were talking through a foghorn and you were holding the horn up to your mouth and you speak, your energy goes forward in a forward direction that represents a gain. So we talk about antennas in terms of beam width and gain. And of course, as you should know with a wireless LAN, your antennas could be internal inside the access point or they could be external. And so if you're deploying an external antenna, then it's really important that you need to understand how to choose that antenna, how to read those specifications. And so it's very important for external antennas that you know how to read in terms of beam width and antenna gain when you're reading those specifications. So to understand antennas, we need to start with the isotropic antenna. And an isotropic antenna is a theoretical antenna, i.e. it cannot be built. And the reason is that this assumes the antenna is this dot in space and that it's evenly radiating in this perfect sphere. So in every direction that waveform is radiating out and is equal in every direction. And so as it radiates out, that sphere gets bigger and bigger and bigger. And so when we talk about forming patterns and focusing energy in different directions, we talk about it in reference to the isotropic antenna. And that's why normally when we talk about antennas and we look at antenna specifications and we talk about antenna gain, the antenna gain is represented in dBi, i.e. decibel gain relative to an isotropic antenna. Now, so for an isotropic antenna, it radiates out like a perfect sphere. Now imagine if you had a ball and it's a perfect sphere and you put it on the table and you press down at the top. What happens is that it starts to push out at the sides and forms like a donut type shape. So the surface area stays the same, but it forms this kind of donut shape. And that's an omnidirectional antenna. So an omnidirectional antenna has a gain relative to the isotropic antenna, but is forming that donut type shape, and that's what you want if you're deploying an access point covering something like an office area where you want to cover the whole floor area and you want a 360-degree circular pattern, but you don't really want to be radiating down to the floor below or the floor above you. So you create this omnidirectional, this donut type shape, and it gives you a gain relative to the isotopic antenna. Then you have a more directional antenna. If you look at the pictures here, you can see Yagi antennas. This is very much what you'd have if you had TV at home. I listen to the free radio TV stations, and so therefore I have a Yagi antenna. And I just point it at the various directions until I get the strongest signal, and then I pick up various radio stations. In the bottom right-hand corner of this picture, sitting next to the bird, is actually a semi-parabolic antenna. Both the Yagi antenna and a semi-parabolic antenna are what we call directional antennas, and they focus the energy in a specific direction. So like I was saying with the Yagi antenna, I point it in a certain direction, and so it's able to receive more energy coming from that direction. But if there was a transmitter 90-degree angle to it, then I'm not going to be picking up that signal because I'm really focusing the energy in one direction, and so trying to pick up signals or transmitting energy in that direction with a directional antenna. So another term that you need to be really familiar with is the effective isotopic radiated power, what we refer to as EIRP. When you look at regulators around the world, they will regulate the spectrum, and those regulations vary depending on what frequency, what spectrum you're using. And what they typically regulate is the transmit power level from the transmitter, and they also regulate the radiated power from your antenna. And so it's important to understand how to calculate what the radiated power is from your antenna to make sure you're meeting your legal regulatory requirements. So in this picture here, I've got my transmitter, and let's say my transmitter is transmitting at 20 dBm. For those of you not familiar with dBm, we will be discussing that in a little bit more detail a little bit later on. But 20 dBm is 100 milliwatts. So if I'm transmitting at 20 dBm from my transmitter, and then that signal is going up the cable to the antenna. Now, as it goes through the cable and the connectors, it's going to suffer some loss. And so let's say I get a 1 dB of loss. I have to take that away. So that would be 20 dBm minus 1 dB. Then I get to the antenna, and let's say in this example I'm using a parabolic antenna like the example shows, and let's say the gain of that antenna relative to my isotopic antenna. So remember, my isotopic antenna is that perfect sphere, but here I'm forcing all my energy with a parabolic dish into a long beam. So let's say I have a gain of 15 dBi. Then my effective isotopic radiated power would be my transmitter, which was 20 dBm, minus my cable loss, which was 1 dB, plus my 15 dBi antenna gain. So there's 20 minus 1 plus 15, which is 34 dBm. So in this scenario, I would have to make sure that the frequency I was operating on would allow me to both transmit from a transmitter at 20 dBm, i.e. 100 milliwatts, and my effective radiated power was 34 dBm.